So what happens here is that first we take x0 and x1 and concatenate them. x0 and x1 are numpy arrays. And after that we perform a feature union. We perform a feature union of finding the single best feature and also taking the first two principal components. After that, we construct a random forest predictor, and then we make a pipeline combining all of these things together, and then we run fit and predict and all the regular things that we usually do. Now, if we look at this, if we look at the outcomes and the intermediate steps, we'll see just many numbers. So, for example, if we look at x0, it's basically just a bunch of numbers inside an numpy array, and if we look at x1, it's also a bunch of numbers. And of course, concatenating them together just gives several more numbers. And if we try to look at the outcome of this and look at what forest feature importance is, it just gives us another bunch of numbers. And that's a bit of a problem because it's very difficult sometimes to interpret what these numbers mean. For example, if we run feature importances and we see that we got these numbers 0, 1, 0, 3, and 0, 7. So to which original features in x0 and x1 do they even refer? And given that the first of these is select k best, which is a concatenation of x0 taken from x0 and x1, so do we even know if it's been taken from the first one or the second one? It's very hard sometimes to understand what these things mean. And even more than just interpreting the results, it's sometimes difficult just to get the thing working correctly. So here's a mistake that I once made. It could be that in the training, what you have is that x0 and x1 come from two different databases, and you load them up and concatenate them and train your model. But once you have your model fitted and you want to deploy it, then the data is coming somehow different entirely. Maybe it's coming from the internet, and you just take it and then run a predict on it. And because Scikit-Learn basically will just check for dimensions, then as long as the dimensions fit, it's okay by it. But it has no way of knowing if you've concatenated the columns the right way, and you might make a mistake there and slip it around, and it'll be just happy with what you give it and outcome a prediction, which might not make sense at all. The second example I'd like to give is the case where you need to perform data munging in the middle of the pipeline. So here is a matrix of the classic movie recommendation system. This is data from an actual field survey I've taken with my three daughters over the movies Shrek, Mulan, and Frozen. And in this case, what we'd like to do is to run a grid search CV, and in each fold of the grid search CV, we'd like to perform NMF, non-negative matrix factorization, followed by random forest regressor. So Scikit-Learn is an excellent library, and it gives us a step that performs NMF. But the problem is that this matrix is not in the form where we can apply the NMF directly. So what we need to do is as follows. We take the original matrix, which has a column per user, a column per movie, and a column per the rating. And then we need to pivot it so that the rows are users and the columns are the movies, right? And once we've done that, only then can we feed it back and can we feed it into the NMF step. And the NMF step will give us the latent variables explaining the users and the movies. But actually this isn't enough because now we need to take this matrix back and go to the original matrix and somehow concatenate it. And only after we've done this concatenation do we have the matrix in the form where we can pass it on from the NMF over to the random forest regressor. So Scikit-Learn is an excellent library, but it's a library for machine learning. It's not a library for data munging at all. Nothing in Scikit-Learn will help us do this really. And in some respect, the problem is that Scikit-Learn basically isn't even built for understanding metadata. One moment, please. Scikit-Learn isn't even built for understanding metadata. So if we look at the columns of explaining who are the users and the movies, 1 second please while I find place. Okay, so the problem is that the user and the movie columns are not really describing data at all. They're describing metadata, and Scikit-Learn doesn't really know how to do it. In fact, Scikit-Learn can't even take columns that take things that aren't numeric. So there are ways of fooling it by somehow encoding this as numerical values and then telling Scikit-Learn, ignore these columns. But there's something very unnatural about it. Finally, the last thing is, which is orthogonal to the first two, is the combination verbosity. So here you can see graphically the result of taking select k-best together with PCA and fitting it into a random forest regressor. And to me, it looks like the following piece of code is just too long and not readable enough compared to what a basically simple thing is being done here. So fortunately, all that's needed is really to build and connect together things that other people have done already. For the first thing, a numpy array is basically just an array of numbers. But Python does have de facto a standard construct for tabular data together with metadata. That's basically Pandas. I think it's used sort of universally. So here we can look at how the iris how the iris data set looks. So first in numpy form and then in Pandas form. And in Pandas form, it's much more clearer what we're seeing here. The second thing in regards to combinations is that the Unix pipeline has for many years a system where you can pipe things from one stage to another using the pipe operator, and that's very succinct and easy to work with. So now in the next two sections, I'd like to describe a library which we've built that addresses these two things. First, I'll describe the interface, then a little bit about the implementation, which will be a bit more Python oriented. So the library is built of two levels. There's a low level, which you shouldn't need to use most of the time, which basically contains a mixin and an adapter. And then there's the higher level that automatically wraps all of Scikit-Learn and XGBoost and TensorFlow. So let's start with the lower level. It just contains a function and a mixin. It works this way. Suppose you take an Scikit-Learn compliant stage. For example, you take Scikit-Learn linear model, linear regression, and you call the frame function. So what it'll do is to devise at runtime a new class that subclasses both the original class that you've given it and the mixin, ibex frame mixin. And this resulting class that subclasses both of them gives us two things. For the one, it understands now metadata. So it takes only Pandas data frames in series. It outputs only the Pandas data frames in series. For example, if we fit it on the matrix X, which is indexed by 0, 1, 2, and Y, which is indexed by 0, 1, 2, and we fit it, and then we ask it to predict what will be X, so it'll give us a series, not a numpy array, and it's indexed on 0, 1, and 2 because we're saying those are the predictions for these specific instances. And likewise, it also does this for columns. So for example, if we give it X and Y, where now the columns, let's focus on the columns of X are A and B, and we fit it on X and Y, and then we ask it to predict X, but we invert the order of the columns. Then, since logically a data frame is closed under permutations of the columns, then it doesn't care that the columns are in the wrong order. It'll output the thing that we expect it to do, because the columns now carry the metadata. And another thing it'll do, though, is to check the consistency of the indices. So, for example, suppose now we try to repeat what we've done before, but we feed it the matrix X, which is indexed by I, J, and K, and Y, which is indexed by 21, 22, and 23. So obviously something has gone wrong here, right? Because what are these instances? Are they lettered instances or numbered instances? If we try to do this, then it'll raise an exception saying that, it'll throw an exception saying that it doesn't understand what we want to do. And likewise, in terms of columns, if we feed it X and Y, where X has the columns A and B, and we fit it on that, and then we try to predict X1, which has the columns M and N, then it'll raise an exception and say that it doesn't understand what these columns mean. It's obviously now operating on different features than it's been trained on. Here again is the iris data set in Pandas form. So if we take now an SVC, a scalable, support vector classifier, and we ask to fit it, and then we ask what are the coefficients, then we won't get a numpy array. Instead, we'll get a Pandas data frame. And I think this Pandas data frame is much more interpretable. We can see that the coefficient of Sato's sepal length, for example, is in the top left corner. So we don't really have to guess anymore what we got. The second thing that the resulting class, which subclasses these two classes, gives us is the optional ability to combine estimators in a way that is more succinct. So instead of calling a make pipeline, it's possible now just to use the horizontal bar, the pipe symbol, and this does exactly the same thing. Frame PCA and components 2 piped into the following stage is exactly the same as calling make pipeline. And similarly, instead of calling make union, we can optionally use the plus. Optionally use the plus sign. So combining these things, if we look at the previous example that we've seen of taking a feature union of select k best and PCA and feeding it in to a random forest regressor, so now we can just write it very succinctly like this. It's the addition of the first two features piped into the last estimator. And in conjunction, these things work even better together if we use the metadata together with combining many different steps. So for example, if we take again the iris data set in the data frame form, and now we perform PCA plus select k best, and then we do transform on it. So it'll tell us that the result is PCA, which has component 0 and component 1, and select k best, which in this case chose petal length in centimeters. So Pandas is really good about all of this hierarchical data. It knows how to organize it. So this just basically works here. And taking the example that we've seen before, suppose we take select k best and PCA and we feed it into the forest. And then after fitting it, we ask the forest what are the feature importances. So instead of just giving us numbers, it'll give us a Pandas series, and it'll say sepal length was 0.09, and it gives names to all the rest of the things. Another problem we encountered before is what to do if we want to write a stage that does Pandas manipulation in itself. When we saw the movie recommender system, what we needed to do is perform pivots and merges and all sorts of stuff like that. But in this case, there's not really a problem, because if you write a class on your own and you just subclass ibex.frameMixin, then all of the methods fit, predict, and so on, they will just take now data frames, not series. And when in the internal body of the code, now that you have data frames, you can use all of the regular Pandas goodness that you're used to. So I think it's a good way to combine all of these things. Okay, the second layer basically automatically wraps Scikit-Learn, TensorFlow, and XGBoost for now. And it's necessary for the following reason. As we've seen before, we can use the lower level frame function to wrap up things. So if we take select k best and call frame, then we can get a result. And if we call linear regression and apply it to frame, then we can get a result. And each time we call frame, we can get another class. But that's a bit tedious. It can get pretty annoying to have someone use frame over and over again. So in order to avoid this, the library basically automatically wraps the aforementioned library. So all you need to do is, instead of importing Scikit-Learn linear model, you can import instead of it ibex.scikit-learn.linear model, and then you'll just get all the regular estimators you're used to, but they will be in data frame form, in Pandas form. And the same thing for XGBoost and for TensorFlow. In fact, you can import simultaneously in the code both classical Scikit-Learn and ibex Scikit-Learn. They really don't bother each other, so this doesn't break any of the code. It doesn't modify any of Scikit-Learn. They work well side by side. Okay. Now in the last section, what I'd like to do is to discuss a little bit of the implementation of it. At this point, it becomes a bit more of a Python talk than, I don't know, machine learning or scikit-learn sort of talk. So how do we really write a library that wraps up estimators the way Scikit-Learn does? So the straightforward approach is just to use composition, right? So for example, suppose we have some base estimator, and now we'd like to write a wrapper on top of it. So we'd write a class wrapper, which takes base estimator, regressor mixin, and the frame mixin. And inside it'll hold an object of the original thing that it's wrapping, and then basically it'll just delegate everything to the internal object, right? So the internal object knows to talk numpy, and the external object we want needs to speak Pandas. And it'll work as follows. Suppose the user calls something like predict. So it calls predict and sends it over to the wrapper class. The wrapper class will validate things. It'll check that it's the appropriate type, that it's a data frame and a series, and so on. After that, it'll strip all of the metadata out and just retain the numpy arrays and send them over to the wrapped class. The wrapped class will return a result, and then the wrapping class will add again the necessary indices and stuff and send things back to the user. So that's the way I thought of approaching it in the beginning, but this really didn't turn out to be so feasible for a number of reasons. The first reason is that Scikit-Learn is just too big a library, and it's too dynamic a library. This is a code flower type representation of the Scikit-Learn in the version that I'm using, and you can see here that there are dozens of different classes, and moreover it's dynamic. Each time you upgrade the version of Scikit-Learn, then some modules and classes are added and some are removed and so on, so it's not really possible to wrap it on one side and then ship it and have it done on the other side. The way to approach it is to do these things at runtime. So it goes as follows. Here's an interesting thing, at least for me, about Python. When you write a compound import statement, meaning if you write something like import ibex.sklearn.linear model, so the runtime environment is going to translate this into a series of import calls. So first it's going to call import ibex. After that, it's going to call import.ibex.sklearn. At this point, we can do something nice that the runtime environment lets us do, which is to register a class in sysmetapath. So the way this works is that we can take a certain loader class and go to sysmetapath and install it as something that from now on things need to run through it once an import is called. So after this is done, when the runtime resumes its import and calls the full length of import ibex.sklearn linear model, then basically it's running through our class which intercepts it. And at this point, the class is going to use the Scikit-Learn installed on that system and call dir. And the directory is going to return the list of all the members. And then we can see here, for example, that it has the all variable and ARD regression and so on and so on. Some of these things are functions and some are classes which we want to wrap and some are not. And another useful model to use is inspect. So the way inspect goes is that you can take all sorts of stuff and ask, is this thing a class? Is this thing a function, a variable, and so on. And once the runtime tells us what is in the specific sklearn linear model on the system in which it's running now, and inspect can filter out the things that we want to wrap, then we actually perform the wrapping. And this way it works basically for every system differently. Okay, another thing that's a bit unique to Scikit-Learn is that it's a bit finicky about its constructor. So for example, you cannot write a Scikit-Learn stage whose init function takes args and kw args. If you try to do this, then the runtime of Scikit-Learn will complain. So it's not that easy to write a generic wrapping class. Another thing that's a bit unique to Scikit-Learn is that it has attributes that get added while it's executing. So for example, if you take a linear regression stage and you try to call the coef attribute, then it'll tell you that it doesn't have any such thing. But if you do fit and then try to call the coef attribute, so it'll say, oh, great, I'll give you now the attribute. So you can't really scan the class once you load it and ask it what attributes do you have. It depends what you do with it. As you do with it different operations, then various attributes will be added. So there are several ways of dealing with it, but the way we chose to do it is by using local classes. So for example, let's look here at line 1 at the logistic regression class. And the logistic regression class has two things that are unique to it. The first is it has an initializer that's very specific to it. It takes penalty equals L2, dual equals false, all sorts of stuff like that. Different estimators will have different initializer arguments. And the same thing is that at some point in the code, it says self.n iter equals something. Once you fit it, it's willing to tell you how many iterations it took. So our code takes this estimator and it builds a local class. And the local class, whose code is written inside the function, basically derives from this estimator and the frame mixin, but it doesn't supply its own initializer. So now when you try to instantiate this, or to call n iter, so both things fall down to the base class. And they drop through to the base class, and this way they're handled appropriately to the class that was used to call this function. Using local functions has its own problems. I did not know this at the time, but you cannot pickle classes that are defined locally within a function. So if you try to run this code, the function foo in lowercase inside makes a new class called foo with an uppercase, and you try to take this and to pickle it, and the runtime will tell you that it's not willing to do that. And this isn't just an esoteric problem, because each time in Scikit-Learn you use a higher order function, for example, cross-val score, and you send it some estimator, then it's going to pickle it. And the reason is that cross-val score and all the other cross-validation and so on functions, they have the ability to work on different processes. And basically the only way in Python to get things to work in a truly multi-threaded way or across different processes is to try to pickle stuff and to send them over to the other processes. So because of that, pickling is not exactly an esoteric thing. So another nice thing that the Python runtime gives us, or actually it's the Python data model in this case, is the reduce function. The reduce function is a special method that a class can provide, which says what is the way it would like to be serialized. So basically, this function returns all the code that explains how to wrap it, and each time it's serialized and deserialized, then it has exactly the information that it needs to reconstruct itself over and over. There are a few other problems. For example, local class names, the names of classes defined inside functions are pretty ugly. If in the interpreter you try to ask what the name is, you got a gibberish string. And there's also a problem in partially overriding attributes. So if you call some of the estimators, then some of their attributes are needed inside in order to function well, and Scikit-Learn expects these attributes to be in the form of numpy arrays. But on the other hand, in terms of the interface, we would like them to be at the same time Pandas entities, data frames and series. So there's a problem of partially overriding attributes, like saying when the class needs to use this attribute, then it should be one thing, but when the user would like to see what the attribute is, then it should be something else. And there are lots of hacks to solve this, and I basically found all of them on Stack Overflow. So basically, this is what I wanted to talk about. I tried to show two things. The first is I think that there's a need and also a feasible solution for having a library that basically wraps Scikit-Learn on the fly and gives it Pandas capabilities. It makes code that is safer, it's more interpretable. It allows to combine estimators better, or at least more succinctly. And the more complex things you do with it, for example, if you do nested cross-validation or things like that, then the more you're basically going to need metadata, and the natural way to send metadata is through Pandas data frames, not by hacks inside numpy arrays. So the more you combine these things, I think there's more of a need for it. And in this sense, I think that that the solution fits the current generation of libraries which give a Pandas interface, but have an implementation that works over NumPy. So, for example, if we look at the field of plotting, so we have matplotlib, which works directly over NumPy, but now we have newer libraries such as Bokeh or Seaborn, which reuse the code inside matplotlib, but they work on Pandas entities. They use the metadata. So basically, the solution is the same. And in terms of implementation, I at least thought it was interesting to see all the different utilities that Python gives us. There's this meta path, which allows us to create different paths in the way that new models are imported, and dir, which allows us at runtime to introspect a model, and inspect, of course, and local classes, and the pickle protocol. So the code is really ready to use, and I'd really like to ask you to use it and give us any feedback you have in order to make it better. Just feel free to open issues or anything, or if you want to contribute, I'll be extremely happy. I think it's really time to have a machine learning library that's built over data frames. So that's it, basically, and thank you very much. Yes?
Sorry, maybe I missed this, but when you were talking about the interface for like munging and add estimators pipeline, is there a reason that you didn't stick with like a Scikit-Learn pipeline as opposed to like plus or like Python?
So, yeah, so that's an okay. So the question was why change the way to combine estimators and not reuse the Scikit-Learn solution? So that's an excellent question. It's actually an orthogonal part because you can use all of the metadata stuff without doing that. And I'd like to emphasize that it's completely optional. You can continue to use make pipeline, make union, and so on. I personally find them less fun. If you just have a Jupyter notebook and you want to try out things quickly, it's a lot of typing, I think, relative to what it does. But it's possible to continue using those functions with these classes. It's not a problem. Thanks. Yes.
So you're using the index of the data frame. Is it possible to have a ranking index?
Yes, absolutely. The question was, is it possible to pass multi-index? And the answer is yes.
And then on top of that, can you use the metadata in the index or the multi-index for anything, like for a stratified transaction?
Yes, that's an excellent point. In fact, this was, I think, the first motivation for me. You can use the metadata inside the index to perform more complex things in internal stages, like making stratified or labeled cross-validations, or stacking. There was an interesting stacking talk yesterday. So it's actually designed for that. And if you have such use cases, I'll be really happy to know if it works for you conveniently or otherwise. And if not, please open an issue and say why. Any other question? Yes?
Have you explored the package dill, which sort of expands pickle to allow you to pickle other things?
Right, that's also an excellent question. Dill does pickling much better than pickle does. And why not just use dill? So this goes a bit beyond my knowledge of Python, but as far as I know, it's really a bit risky to assume that you're using dill because it involves a certain order where you're importing things. And I just didn't want to rely on that. But I agree with you that basically it's a better idea to use dill than pickle directly. In fact, from looking in the code, it seems to me that Scikit-Learn itself is using dill internally and joblib and stuff like that. Okay, if there are no more questions, so thank you very much for your time.